Hey, welcome back to discussion 28. This is problem 1. So we're told that workmen are using a bunch of pneumatic tools. It creates a noise 88. If one tool creates a noise level of 88 decibels, which is a few meters away, calculate the noise level if 4 such tools were in the operation the same distance away. So the approach to this problem is basically we have to use the sound level formula where we have this relationship between the intensity of what we're given and then a known intensity as our baseline. So we could break this apart. Right? Before we go too far down the rabbit hole this way, we could actually just say that we know that the initial sound is 10 log times log of 10, 88 over 10, right? This is actually equal to 10 log 10, 8.8, which is equal to 10. This is log base 10 of 10 to the some power, right? So times 8.8 is equal to 88, right? Right, so using this sort of relationship with all of the others, we can say, well, what is the total sound level? Well, it's going to be what would we do? We would take each tool. So this is going to be the sum inside, because we want to sum up the intensities, not the decibel level. The decibel level is on a logarithmic scale. The intensities are a little more straightforward. So we can take each intensity and say, all right, so the first one we're given is 88 over 10. Next one is 88. They're all at 88, right? So that means that we have this relationship. You could just plug that in directly and find the answer. It might be worth looking at this a little closer. This is the log of the number of sources plus 10 log 10, 88 over 10. And for a bunch of sources that have the same decibel level initially, we can do this. 10 log 4 plus, and this is just going to be your initial sound level, right? Turns out this is about 94 decibels. Let's see, it's 94.3. 94.026. So 94. We have this relationship here. So if you have a bunch of sounds that are essentially the same decibel level and they're coherent, your net level is going to be 10 log times the number of sources plus the initial sound source. Say like this would be like one of them. So it would be, this is the increase in your level. So you take one of the sources, one level, here is 88 decibels, and then 10 log the number of sources. That gives you the answer. Okay, next problem. We're given an output power of 4 times 10 to the negative 3 watts from a bell, radiating uniformly in all directions. What is the intensity of the wave 100 meters from the bell? Well, we have this relationship where intensity is the power output over the area. And in this case, we're talking about a sphere because we have a sound and it's radiating uniformly in all directions. It's coming out this way, down this way. And if we look at it straight on, this is 100 meters. So the area of a sphere is 4 pi r squared. So this is going to be 4 pi 100 meters squared. So we just plug in this value. And we end up with now this is interesting because it seems super low, but if you look at there's a standard table of intensities, and in fact there is one in the book, figure 17.2. And if you look at that, you'll see that this actually fits pretty nicely. We're talking 100 meters away from the bell, right? It's at a fairly low power. And this actually is something you can hear. So I recommend looking at the table. This actually fits, and you would definitely hear this. 100 meters, what, like 300 feet away. Okay, next part of the problem. We're given that we're in a factory and there's 100 machines. They produce a sound intensity level of 120 decibels. What would the sound intensity level produced by one of these machines be in the same factory? So we're assuming that all of the machines output the same intensity level. And so we can use the method that we just used before, where I was talking about the number of sources plus the initial source. Right? So really what we want is this. We want to know what is the output of 1. So the easiest way to do this is to say, well, we have 100 decibels, 10 log, and 120 decibels, 10 log n. But over here we take minus L1. No, we don't. We take minus what I just moved. I don't know why I moved that. This is equal to L1. Excuse me. So 120 minus 10 log 10. This is 100 sources, right? So it's 10 to the 2 equals L1. Well, now we're left with 120 minus 10 times log of 10 to the 2, so it's 10 to the 2. That's 20. This is equal to 100 decibels, and that is your answer. So they're pretty loud machines overall. But the interesting thing about this is how sound level works on a logarithmic scale. So if you have one machine that's operating at 100 decibels, you get 100 more machines, and your overall sound level is only going to be 120 decibels. That's still super loud, by the way. You will still damage your hearing with 120 decibels. Easily, quickly. You might go deaf, actually, right away. It's important to know that 120 dB is dangerous. 100 dB is only sustainable for almost no time, for a very short time. A car and a bicycle are traveling directly towards each other at different speeds. So here we have a car, here we have a bicycle. That's a really bad bicycle. Let's go like this. Like this. There's a seat. Okay, it's a nice bicycle. So these are traveling in opposite directions. We are given a speed of the car, 15 meters per second. We're told that the cyclist hears 467 hertz. And the velocity of sound in air, right? We know velocity of sound in air is 343 meters per second. That's sound. Okay, and then it says calculate the frequency of the signal emitted into the air by the moving car along the straight line joining the car to the bicycle. So I'll be honest, I'm not sure what it's actually asking here, because what we have, we're told that the car horn has a frequency of 440 hertz. We're told that in the problem. So if this thing emits a sound at 440 hertz, we can just plug that into the Doppler equation and get what this guy is hearing. You should get this value. So what I'm assuming then is that we have an observer standing on the ground And we want to know what is the sound for the observer. Okay, and we can do that. We have someone standing on the road, and we want to know what they observe, right? So what is the frequency that they are observing? We have the speed of sound. This is all in the book, by the way. We have a few different relationships to look at. You could also just do it this way. The standard, let's just do it this way. The standard Doppler equation, the Doppler shift equation, is frequency of the observer is speed of sound plus minus speed of the observer, right? So if our observer is moving at 0, if this guy is not moving, then this is just going to be 0, over the speed of sound minus plus speed of the source times the frequency of the source. Okay. So what's important here to remember is that you're told that we consider, okay, so if these things are moving towards each other, then we use this, right? And then we also use the one on top here, if they're moving towards each other. If they're moving away from each other, then you choose the opposite sign convention, and you choose the signs on the bottom. I'll show you what I mean. So F observer is equal to speed of sound. Remember, this is going to be 0 for the man standing on the road. So this just goes away. We would say plus 0, right? Doesn't matter. Over the speed of sound minus the speed of the source times the source frequency. And so this gives us 343 over 343 minus 15 meters per second times 440 hertz. That's going to give us a value of 460 hertz. Okay, that's the sound that is being emitted by the car as it's traveling, and let's say it's just passing by a person here. So I'd like to point out that the reason we have this as negative, again, because we have the speed of this car, it's emitting a sound that travels at 343 meters per second, but this is also traveling at 15 meters per second, so we take the difference here, and that gives us the speed that the sound is actually traveling. Okay. And then likewise, if this thing is moving away, right, if this car is moving 15 meters per second in the opposite direction, sound, and then someone is standing over here, the sound is still moving over here at 343 meters per second. So we add those up because now we have a gap, right? So we have 343 plus 15. Okay. And again, there is a much better explanation in 17.9 in the book. It's page 508. Or there are any number of sources online that you can look up where they show examples. There's a lot of nice videos where they actually demonstrate this concept. So I recommend looking at stuff like that if you are at all confused about the sign conventions, because I remember being a little bit tripped up by that when I was in undergrad. Okay, so the next part, we are asked to find the velocity of the bicyclist, right? So back to this situation, let's ignore this guy. Now the car is moving the same speed, 15 meters per second. This thing is moving with some speed unknown. We're given the observer frequency here, we're given the source frequency here, and we just have to plug in and solve. So part B is going to be, oops, we know what this is. F observer is 467 hertz. We're told that, right? Speed of sound is 343 meters per second. We want to say that this is plus because they're moving together. They're moving towards each other, I mean. Okay. And this is minus because they're moving towards each other. So 343 minus 15, it gives you 328, right? And then we multiply this by the source frequency, 440 hertz. Excuse me. So if we're solving for V obs, then we go 460 over 440, right, times 328 minus 343. That's going to be V observer. So I just solved. So I just plugged all this in and solved, right? I solved for V obs. That gives us 5.12 meters per second, which means that the bicyclist is traveling at around 15 miles per hour, right? Which is very reasonable for a bicyclist. So I trust that. And just again, I'd like to make a point of mentioning that for D3, it's saying what is the frequency of the signal emitted into the air by the moving car. Well, sound, the whole point of a Doppler shift is the sound is not absolute. So you have a source frequency and then you have an observer frequency, and those are what you use to figure that out. So I had to make the assumption that we were asking about a stationary observer in the road. Okay, so I think that makes sense. So if you're just standing in the road, and it said along the line towards the bicycle, right? So if you're just standing in the road, like closer to the bicycle while the car's coming at you, you're going to hear it at 460 hertz. All right, next problem. What frequency would the cyclist hear if the car and the bicyclist were moving away from each other, same speeds with which they were approaching each other in the previous part? Okay, so pretty much we're given the same setup, but this time the only difference is the direction of the velocities, right? Here's the bicyclist going this way. So what we're being asked is, what is the frequency going to be here? We know the speed here is going to be 5.12 meters per second. We know that this velocity is equal to, 15 meters per second. We know that the source frequency is 440 hertz. We also know that the speed of sound is 343 meters per second, right? And it's going to be traveling this way towards the cyclist. So let's set up our equation again. V sound plus minus V observer, V sound minus plus V source, right? So this is V source. This is V observer, just to be more clear. And then this is going to be the source frequency, right? Which is 440 hertz, which is an A, by the way, for anyone who likes music. Okay. So now we just plug in and we solve. So, but before we do that, let's just recall again that this was positive if they were moving towards each other, if both of them were moving towards each other, and this was negative if both of them were moving towards each other. Now that we know they are moving directly away from each other, we actually use the negative sign, and we use the one on bottom here as the positive. Okay, so that gives us then what we need is Vs plus Vobs. Let's just write it in. 343 plus 5.12 over 343, oops, see I just messed up. It's minus 5.12. Right, we're moving away from each other, we use the minus sign. Moving away from each other, we use the one on the bottom here as the plus sign. So that's going to be plus 15 times 440. That's going to equal, that gives us a value of, plug it in, 415.27 hertz. So that's a lower frequency, that's what we would expect. And that makes sense. Okay. So I think there's actually, if you had, just to kind of go over this plus minus V observer V source minus plus V source times frequency source, right? So what I was going to say is, excuse me, is if this thing were traveling this direction and emitting a sound this direction, and then this guy here was traveling this way, what would be the frequency here? Really, I don't really care to go through all of the calculations. I'm just saying, what is the sign convention that you use? Well, this thing, the sound is traveling this way, right? The source is traveling this way because our observer is over here, right? So that means that we use the plus, oops, because they're traveling away from the sound, we use the plus sign on the bottom. And since this guy is coming towards the sound and the sound is coming here, we would use the plus sign on top. So then you would get plus like this over plus like this times 440. Okay, and then again, if this guy were traveling this way, the sound's traveling this way, and then the bicyclist is traveling away, what would be the frequency that you would hear? You would get something like this. So we'd go, well, he's traveling away from the sound, so we actually get plus on top. So this would be V observer. And then if he's traveling, if this source is traveling in the same direction as the speed, we'd get minus, right? So V source minus V source. Or sorry, V sound minus V source times frequency. So that's kind of how those sign conventions work. And again, if you're confused, there are more clear explanations, I think, in the book and also online. Okay, the next problem. A wave is moving on a string, and the equation is given here, 0.15. And we're asked to find the wavelength. Okay, well, let's recall that our general form is equal to amplitude sine kx minus omega t. So let's multiply this 10 pi through and figure out what omega and k are, because that would actually be really useful. So now 10 pi over 60 times x minus 10 pi t is equal to kx minus omega t. So that means that k is equal to, what is this, pi over 6, and omega is equal to 2 pi, it's 2 pi frequency. Omega is just equal to 10 pi. I was going to find frequency, but I don't think I need to, so. Okay. But also we want to find wavelength, so wavelength is 2 pi over, sorry, k is 2 pi over wavelength. This is the basic identity that we have. And so that's also equal to pi over 6. So then we just solve for wavelength, and that's going to give us wavelength is equal to 12 meters, so d. And then we go the speed of the wave. Well, speed of the wave is equal to omega over k, remember. And omega is, what did we have, 10 pi. K is going to be pi over 6. So that means it's going to be 60, because these cancel and this goes on top. This is 60 meters per second. So that's number E, or letter E. So those are my answers. Okay, thanks. I think we have one more lecture left.